All right, let's dive right in. Today, we're zooming into the world of molecules to tell a tale of two reactions. It's a fundamental story about how things change, really, and it all comes down to two competing pathways molecules can take when they swap partners. And believe me, that choice changes everything. But why should you care about any of this? Well, have you ever wondered how the complex molecules in modern medicine are actually built? It turns out, the ability to create these life-saving compounds often boils down to mastering the very reactions we're about to unpack. You see, at its core, a whole lot of chemistry is about making and breaking bonds. And so often, it all starts with what looks like a simple trade. One group on a molecule gets kicked out, and another one takes its place. But as you're about to see, the way this swap happens is anything but simple.
So, to really get a handle on this, let's start with the absolute basics of this molecular exchange.
The official name for this process is a substitution reaction. I like to think of it as a little molecular dance. One partner leaves, and a new one just steps right in. The key thing is that the main molecule is transformed, because it's now got a new functional group attached to it.
Now, every good story needs its main characters, right? In our reaction, we've got three. First up is the nucleophile. Think of this as the attacker. It's packed with electrons, and it's looking for a new place to bond. Then, we have the substrate. That's the main molecule that's about to be changed. And finally, the leaving group. As the name suggests, this is the part that gets kicked off to make room for our attacker.
Okay, let's meet our first pathway for this molecular swap, the Sn2 reaction. This is the aggressive, get-it-done-in-one-go strategy.
The name, Sn2, sounds a little intimidating, but it's actually a cheat sheet. The S just stands for substitution, which we know is a swap. N is for nucleophilic, meaning our electron-rich attacker is driving the action. And the most crucial part is the 2. It stands for bimolecular. All that means is that the speed of the reaction depends on two things physically colliding, the nucleophile and the substrate.
Now, the absolute key to understanding the Sn2 pathway is this word, concerted. It means everything happens in one single, fluid motion. The new bond is forming at the exact same time the old bond is breaking. It's like a perfectly synchronized dance move. There's no pause, no halftime, just one step. And because it relies on that collision between two molecules, we call it a second-order reaction. This totally makes sense when you think about it. If you double the amount of attackers in the solution, you're going to double the chances of a collision, so the reaction goes twice as fast. Same thing if you double the substrate.
But what if the molecule isn't in such a hurry? Well, that brings us to our second pathway, the Sn1 reaction. This one takes a much more patient two-step approach.
Just like before, the name tells us the whole story. S is for substitution, N is for nucleophilic. But check it out, the number is 1. This stands for unimolecular. And what that tells us is that the slowest, most important step of the reaction, the one that sets the pace, only depends on one molecule, the substrate itself.
The best way to think of this is as a two-act play. Act 1 is the slow, dramatic breakup. The leaving group just leaves, all on its own. This creates a positively charged and really unstable intermediate called a carbocation. Then, and only then, do we get to Act 2, which is super fast. The nucleophile swoops in and attacks that now vulnerable carbocation.
Okay, so one step versus two steps. Who cares, right? Well, this is where it gets really cool, because these two totally different journeys have predictable and fascinating consequences for the final 3D shape of the molecule.
For that single concerted Sn2 step to actually work, the attacker has to be sneaky. It has to come in from the exact opposite side of the leaving group. We call this a backside attack because the leaving group is essentially blocking the front door.
And the result of that backside attack is just beautiful. The entire geometry of the molecule flips inside out. Seriously, the best way to picture this is an umbrella getting hit by a huge gust of wind. Whoosh! It inverts. That is exactly what happens here. A complete 100% inversion of its shape.
Now, for the Sn1, things get a little weird. In theory, once that leaving group is gone, you've got this flat carbocation intermediate. So the attacker should be able to hit it from the front or the back with equal ease, right? You'd expect a perfect 50-50 mix of products. But when you run the experiment, that's not what you see. You always get a little bit more of the inverted product. So what's going on?
And the answer is just so elegant. It's a concept called intimate ion pairs. It turns out that leaving group doesn't just vanish into thin air. For a split second, it kind of hangs around, physically shielding the front face of the molecule. It's like an awkward X lingering at the front door. That partial blockage just makes a backside attack slightly more likely, which perfectly explains why we get more inversion. It's some seriously cool chemical detective work.
Okay, we've met our two pathways. Now it's time for the main event. Let's put them side by side in a head-to-head showdown to really lock in the differences.
This table really sums it all up. Let's walk for it. Mechanism: Sn2 is one and done, a single step. Sn1 is a two-step process. Kinetics: Sn2 is second order. It needs both molecules to show up. Sn1 is first order. It just depends on the substrate making its move. Stereochemistry: this is a big one. Sn2 gives you 100% inversion, that umbrella flip. Sn1 gives you a mix, but a mix that favors inversion. And finally, substrate. Sn2 needs a wide-open, uncrowded target. Sn1 actually prefers a crowded one because it helps stabilize that carbocation intermediate. They're practically opposites.
We can even visualize the difference in terms of energy. The journey for an Sn2 reaction is like climbing one single steep hill. The very peak of that hill is what we call the transition state, that super unstable, fleeting moment where the old bond is breaking and the new one is forming.
The Sn1 journey, on the other hand, is more like a road trip with a rest stop. It has two hills to climb, one for each step. But in between those hills, there's a valley. That valley represents our carbocation intermediate. It's a little resting point, more stable than the peaks, but still less stable than where you started or where you'll end up.
So the big question is, how does a molecule decide which path to take? Well, it doesn't really have a mind of its own. It all comes down to the specific conditions that chemists create for the reaction. So if you want to force an Sn2 reaction, here's the recipe. You need a strong, aggressive nucleophile that's ready to attack. You need an uncrowded substrate so there's a clear path for that backside attack. And you use a special kind of solvent called polar aprotic. Basically, it's a liquid that won't get in the way and slow down your attacker.
And what if you want an Sn1? You do pretty much the opposite. You use a weaker, more patient nucleophile that can wait for the leaving group to depart. You actually want a crowded substrate because that creates a more stable carbocation. And here you want a polar protic solvent, a liquid that can actually help pull off and stabilize the leaving group, giving it the encouragement it needs to start that slow first step.
And that choice, that control, is everything. Being able to force a reaction down one path or the other is exactly how chemists build the molecules of life-saving drugs, ensuring they have the precise 3D shape they need to work. So next time you think about how things are made, maybe you'll wonder about their journey. Was it a swift, one-step dance or a patient two-step?